Hi friends, welcome back to our online course on non-conventional machining. Today we will learn about electron beam machining. In this topic we are going to cover working principle of EBM, what are the equipments used in EBM, different process parameters, advantages, applications with its diagram. It is a non-traditional machining process in which no physical tool is used. Electron beam machining is same as laser beam machining process in which except laser, high-speed electron beams impinges on workpiece. This will generate high heat energy and melt and vaporize metal from the workpiece. This whole process takes place in a vacuum chamber. It is mostly used to drill holes in any shape. Now I will discuss some history part about the electron beam machining. EBM invented in Germany in 1952 by Dr. K.H. Stringer Wall. EBM is a high energy beam machining process. Again, electric energy is used to generate high energy electrons. The mechanism of material removal is primarily by melting and rapid vaporization due to intense heating by the electrons. So, I have shown in the figure electron beams. Now, here I have shown the line diagram of electron beam machining. You can see the different parts. So I have shown that is a vacuum, how we can give it, then filament, cathode, anode, high vacuum chamber, then focusing coil, and after focusing coil we have the deflecting coil, and that impinge on the workpiece. Now I will discuss about this process. Electron beam, that is a negatively charged particle, is generated in an electron beam gun. Electron beam gun provide high velocity electrons over a very small spot size due to pattern of electrostatic field produced by the grid curve. Electrons are focused and made to flow in the form of converging beam through a anode. The electrons are accelerated while passing through the anode by applying the high velocity at anode. A magnetic deflection coil is used to make electron beam circular and to focus electron beam at a point, that is localized heating. Then the workpiece to be machined is located under the electron beam and is kept under vacuum. After that, the high energy focused electron beam is made to impinge on the workpiece with a spot size of 10 to 100 micron. Then the kinetic energy of electrons upon striking the workpiece changes to heat, and which melts and vaporizes the minute amount of the material. Here I have shown the diagram, that is a localized heating by the focused electron beam, that is first diagram. Then second, formation of the holes. The melting, that is the vaporization of front gradually progresses, and the finally molten metal, if any, at the top of the front is expelled from the cutting zone by the high vapor pressure at the lower part. The whole process is carried out in the vacuum chamber, and the gun is EBM is used in the pulse mode. Holes can be drilled in thin sheets using a single pulse. For thicker plate, multiple pulses would be required. So again, in this diagram I have shown the penetration till the auxiliary support. So you can see there how the drill is produced and how removal of material happen due to the high vapor pressure. Now you may come across the one question, that is why vacuum chamber is required. So the entire process occur in a vacuum chamber because a collision between an electron and air molecule causes the electrons to scatter and thus lose their energy and cutting ability. So this is the main reason behind this why to use vacuum chamber. Now we'll discuss about the electron beam machining equipments or setup. So first component is electron beam gun. So here I have shown it's a figure. So I will discuss about the electron beam gun. So electron beam gun is heart of the EBM. The basic functions of any electron beam gun are to generate free electron at cathode, then accelerate them to a sufficiently high velocity, and to focus them on a small spot size. Cathode is generally made of tungsten or tantalum. Such cathode filaments are heated, often inductively, to a temperature of around 2500 degrees Celsius. Heating leads to thermoionic emission of electrons. Then a combination of repelling forces from the negative cathode and the attractive forces from the positive anode causes the free electrons to be accelerated and directed towards the workpiece. One of the major requirements of EBM operation of electron beam gun is maintenance of desired vacuum. Vacuum is achieved and maintained using a combination of rotary pump and diffusion pump. So here I have shown that diagram. And diffusion pump is attached to the diffusion pump port of the electron beam gun. Diffusion pump is essentially an oil heater. As oil is heated, the oil vapor rushes upward. The nozzle change the direction of the motion of the oil vapor, and the oil vapor start moving downward at the high velocity. Such high velocity jets of the oil vapor enter any air molecule present within the gun. This oil is evacuated by a rotary pump via the backing line. Now second component, that is the power supply. So for EBM, the high voltage power supply is used. The voltage up to 150 kilovolt it is required to accelerate the electrons. The most powerful electron beam machining system are capable of delivering enough power to operate guns at average power level of up to 12 kilowatt. Individual pulse energy can reach 120 joules per pulse. Then to avoid the possibility of arcing and short circuits, the high voltage sections of the power supply are submerged in an insulating dielectric oil. So this is about the power supply. Now we'll discuss some process parameters of EBM. So process parameter which directly affect the machining characteristics in EBM as follows. The first is the accelerating voltage. The electrons get accelerated at high voltage. Then the beam current related to number of electrons emitted by the cathode or available in the beam. Beam current can be as low as 200 microampere to 1 ampere. Next process parameter is the pulse duration. Pulse duration can be as low as 50 microsecond to as long as 15 millisecond, and energy per force. Again, power per force, lens current, spot size. Now this spot size is controlled by the degree of focusing achieved by the electromagnetic lenses. For a lower spot size, the material removal would be faster, though the size of the holes would be smaller. The next process parameter is the power density. The energy density and power density is governed by the energy per pulse duration and spot size. Now here I have shown some formulas which is required to calculate the MRR. So if you want to calculate total penetration range, then you can use this formula 2.6 into 10 to minus 17 in bracket V square divided by rho. So V means the accelerating voltage in volts, then rho is the density of material, then Using the second formula, you can calculate the speed of electron under control of electric field. So small m is a mass of electron, E is charge of electrons, and E is the capital E voltage of electric field. So you will get the V, and from this you can easily calculate the power for beam current. That is a P, capital P is equal to EI, and we will get in watt. After that, you can calculate the force of beam on molten metal, then power requirement for EBM process, which is approximately proportional to the MRR. So we'll get the formula, that is P is equal to C into MRR. C is the specific power consumption. You can take as 12 watt per cubic mm per minute for the tungsten metal, and 7, 6, and 4 for iron, titanium, and aluminum respectively. So this is about the process parameter. Now we'll go for the process capability of this electron beam. EBM can provide holes of diameter in the range of 100 micron to 2 mm with a depth up to 15 mm, that is with a ratio of inner and outer of around 10. There would be a edge rounding at the entry point. So here I have shown the diagram where you can see the typical curve shape of electron beam drilled a hole. Metals such as steel, stainless steel, titanium, and nickel super alloys, aluminum, as well as plastics, ceramics, leathers, can be machined successfully using this EBM process. The heat affected zone is rather narrow due to shorter pulse duration in EBM. Typically, the heat affected zone is around 20 to 30 micron. So here I have shown the figure which describes the variation in the drilling speed with volume of material removed. So metal like aluminum and titanium alloys are more readily machined compared to the steel. EBM does not apply any cutting force on the workpiece. Thus, very simple work holding is required. Holes can also be drilled at a very shallow angle of less than 20 to 30 degree. Now we'll see some points regarding design consideration. The first point is the non-reflective workpiece surface are prepared. Then sharp corners are difficult to produce, so deep cut produce tappers. Then we need to consider the effect of high temperature on the workpiece material. Then parts should match the size of the our vacuum chamber, and we need to consider manufacturing the part as a number of smaller components. So these points we need to consider in the design consideration. Now through the literature review, I have the comparative performance about the different non-traditional machining processes. So here I have shown the table. At one side different processes I have mentioned, then their material removal rates I have given, then approximate unit power, and the relatively capital equipment cost per unit MRR. So if you see our electron beam, so which will give the 0.001 cubic centimeter per second MRR. Okay, so by comparing with the other, you will get the importance of this EBM. Now we'll discuss some advantages about the EBM. So first advantage is extremely close tolerance can be maintained. Then heat affected zone are minimum. It can machine almost any material irrespective of their mechanical property. So here no condition about the mechanical property. The beam can be concentrated on a very small area. It produces better surface finish and narrow curve. And thermal distortion is less. and the process is fast because it is entirely non-mechanical. Now some limitations I have mentioned here. So first is the equipment cost is very high. The interaction of the electron beam with workpiece surface produces hazardous X-ray. Then vacuum is essentially required because of very low MRR. The process is economically only for small volume we can cut. The skilled labor is required to isolate the electrons. Very high voltage is required to isolate the electrons, and the process can machine only thinner parts. Now we'll discuss the applications. So electron beam machining is particularly suitable for producing very small diameter holes down to 0.002 inch. It is especially adapted for micro matching. Major application of EBM include matching in thin materials, cutting of slots, and drilling of the holes with very high depth to a diameter ratios, usually more than 100 as to 1. Machining of wire drawing dies having small cross-sectional area can be done with the help of this EBM. EBM is also used as an alternative to light optics manufacturing method in the semiconductor industries. So this is about the electron beam machining. Now we'll discuss the EBM characteristics. So how this material removal happens? The action is the melting and vaporization. So this process happen in the vacuum medium. Then tool beam of electron moving at a high velocity is used. Then we can achieve 10 mm cube per minute MRR. Then specific power consumption is up to 450 watt per cubic mm per minute. Critical parameters are accelerating voltage, beam diameter, work speed, melting temperature. And this EBM is used for the all materials applications. Then shape application, drilling fine holes, cutting contour in the sheets, cutting narrow slots, and some limitations. That is a limitation is a very high specific energy consumption, necessity of vacuum, expensive machine.